This is chapter 1.3. We're going to talk about our first family of functions known as linear functions. So a family of functions are functions that behave the same way and have the same properties. So this video will focus on linear functions, which you may have encountered before. For the warm-up, we do a notice of wonder activity where we're given some functions, and I can't really notice a wonder for you, so I'm not going to really talk about this. But as you're looking at this problem, just notice how structurally similar these three equations are. And then this fourth equation, it looks different. So that's something you may notice and wonder about. For practice A, we did a gallery walk. So we divided the class into 4 groups. Each group had a different function, and they had to analyze their function, answer questions about it, and ultimately sketch a graph. And then we compared the similarities and differences between each of the graphs. So 3 of the graphs produce straight lines. This fourth function, the one that I said looked different, is not a straight line. It's curving. You may talk about how it's increasing faster and faster as t increases. The other graphs are straight lines, so that could imply something to do with constant rate of change. All 4 functions have something in common. They both show what we call the vertical intercept. So back in Algebra 1, you probably call it the y-intercept. But, the output is not always y. It could be a different variable. So we're going to call it the vertical intercept. So vertical intercept is where the graph crosses the vertical or the y-axis. So for P of A, 20,000 would be the vertical intercept if you were to sketch the graph. Notice that the vertical intercept is where t, or the input, equals 0 for all 4 of the graphs, including this fourth function P of D. Even though the function looks different, we have 15,000 times 1.07 to the power of t. This is actually an exponential function, which we'll see in chapter 4. But the vertical intercept is still shown in the function, which you can see right there. What else? Also, P of B stands out because it is a decreasing function, and that's due to the negative 300 times t that appears in the function itself. This is actually what we call the constant rate of change. So back in 1.2, we learned about average rate of change. But with linear functions, we call it a constant rate of change because it's not really an average anymore. It's every time t increases by 1, we know what's going to happen for sure. It's always going to the function's always going to decrease by 300. Or in P of A and P of C, when t increases by 1, the population will increase by 1,600, or it'll increase by 650. That unit increase is now constantly growing. It's not sporadic. It's constant. It's predictable. So that's that. Now, practice B, some more functions and some more graphs. Each function represents the narwhal population. Yes, we do have narwhals. Enjoy the comic on the right here. So we had to match each function with its graph. So let's break this down. Also, the labeling the graph, the horizontal axis is time, vertical axis is the narwhal population. So you input a number of years since 2020, and you get the narwhal population in that year. Hooray, hooray. All right, so how we match each function with its graph. So looking at n1 of t, we have 500 minus 10t. So as we saw in practice A, this is your vertical intercept, this constant without the variable. 500 is the vertical intercept, or you can think of it as the starting value. is the value, or is the amount of population when t equals 0, when that input is 0. So before any time has surpassed, you have a starting amount of population. You have the vertical intercept of the graph. So you look for a graph that has 500 as the vertical intercept, and there it is right there. It's graph A. And then notice that that graph is decreasing due to the minus 10t. So this is your constant rate of change. For every year that goes by, the narwhal population goes down by 10. According to that model, who knows what's actually happening in real life. Okay, so all these linear functions have that structure. So for n2 of t, we have 250 plus 10t. So 250 is the vertical intercept. 10, now positive 10 is constant rate of change. So now the graph will increase instead of decrease. We'll gain additional 10 narwhals every year. So n2 of t has a vertical intercept of 250. So on the vertical axis, notice that it's crossing at 250. However, graph C, this blue graph, is doing the same thing. It also has that vertical intercept, 250. So how do we decide between if n2 of t is B or C? Because they both have a plus 250 in them. So what we got to do is compare the constant rates of change. With a higher constant rate of change, we should expect a steeper line. So graph B is steeper. It's increasing faster. So that's B. N2 of t is B. Therefore, N4 of t must be graph C. So with the same vertical intercept, it has a smaller constant rate of change. It's not gaining as many narwhals every year. So the graph will be a little bit flatter, a little bit more horizontal. And then N3 of t must be graph D. It's got a vertical intercept of 10, and so does the graph. It has the same constant rate of change as graph C, but a different vertical intercept. So you can manipulate the parameters of each function. Okay, if you change the constant, that moves the graph up and down, but it does not affect the steepness. The coefficient of the variable will affect the steepness of the graph because that's the rate at which the graph is changing with respect to t. Now, because this is a word problem, the vertical intercept and the constant rate of change have meaning, and I've been describing that already. So just to pick one function as an example, in n3 of t, we have 10 is the vertical intercept. It's essentially the starting population of narwhals in the year t equals 0. So before any time has gone by, you have a starting population. And then the coefficient of t, so the 5, that is the constant rate of change. Each year, the population increases by 5 narwhals. So we describe it using that unit increase. Okay, for every 1 year that goes by, population changes by a certain amount. Let's take a closer look at the first function and 1 of t. So a lot of information here. So you fill out a table of values by substituting in these t values, and you should expect a linear or a graph that is a straight line. It's decreasing because losing 10 narwhals every year would cause a decreasing graph. So the population gets smaller and smaller. So what is the purpose of sketching this graph? Well, notice that I sketched the graph so that it goes below the t-axis. So we are now in the negative narwhal population. And in real life, I don't think that can really happen. We don't really talk about negative population. It's more of a positive quantity. So this graph really should not go below the horizontal axis, but it does right now. In chapter 2, we'll discuss the idea of why this cannot happen and how we can make sure it doesn't happen. The graph will, however, realistically, it will hit the t-axis. So it may not go through it, but it will hit it. And this is called the horizontal intercept. It's essentially when the population equals 0. The narwhals have gone extinct. So that's what the horizontal intercept means. You may know it as the x-intercept, but in modeling problems, it's not always x. It could be t. So in general, it's the horizontal intercept. It's that input value that makes the output, or in this case, population, equal 0. And then we're given a table of values. So how can we see from the table that this is a linear function? Like if we don't have the graph, how do we know if it's linear? So notice that the inputs, or the t-values, are always increasing by the same number, 10. So they're evenly spaced. For evenly spaced inputs, or t-values, notice that we have evenly spaced outputs. And I don't know why I wrote plus 100, that should be minus. But anyway, the population will decrease by 100 every time t increases by 10. So for evenly spaced inputs, you have evenly spaced outputs. So plus 10 means minus 100. Again, sorry, I put plus. I don't know what I was thinking there. But again, plus 10 for t means minus 100 for n of t. Evenly spaced inputs give evenly spaced outputs. Therefore, this table represents a linear function. Right, it says it here too. Okay, that's how you see the constant rate of change. So for our summary, we defined what a linear function looks like and what different parts mean. So in general, you have f of x equals b plus mx. B is the vertical intercept. It occurs when the input equals 0. It's that starting value. Of course, the input is x, let's say. The output is f of x. The coefficient of x is m. You may know it as slope, but in pre-calc, we'll call it the constant rate of change. So it's still slow, but we're not going to call it that. So we define the vertical intercept as when the input is 0. The horizontal intercept is when the output is 0. Tables for linear functions, they have evenly spaced inputs, or x values, that give evenly spaced outputs, or y values. So in this example table, when you increase the input by 3 every time, notice that the output, or f of x, increases by 6 every time. So when the inputs are evenly spaced, they're 3 units apart, that guarantees that the outputs will be 6 units apart, which are still evenly spaced. So evenly spaced inputs gives evenly spaced outputs, therefore it's linear. And then the graph of any linear function is a straight line. So notice that this is your vertical intercept when x equals 0, or the input is 0. And then your horizontal intercept, it's when the output is 0. The graph's on the x-axis. And that's the lesson. Thank you for watching this video. Have a great day. Go Riders.